Sir, it is little bit better, but I need to do physiotherapy regularly now. ACL complete tear. Good morning. So in last class we were uh, hello. In last class we were for in explainability of AI models, where in SHAP analysis there was some disagreement, confusion. So I have collected a published data, a published research paper in area of mortality prediction in septic shock patient in ICU. This paper was published in 2023. It is in AIMS, on AIMS dataset. And from this SHAP bar chart, you can see the different parameters that were used for the model. So it was a vast list of parameter. Uh, it was not accommodated, it could not be accommodated in a slide. So I did not add it. It was a long list of parameter with all ventilator, everything, all kind of data set. So these was top some 25 parameter in the SHAP analysis list, and it is showing the bar plot. The more important feature for model prediction is at the top. That bar length is showing the SHAP value. So here the SOFA score, that is clinical standard for predicting the risk factor in septic shock patient, is coming out to be the best parameter here. So it is clinically also acceptable thing. The SOFA is coming the most important parameter, and we compared the model with SOFA, and there was little bit more uh, increment in the area under the curve for the classification of mortal, means the patient who died and the who survived. And in this summary plot, that is called density scatter plot, the values are showing each data point of from each patient. So SOFA score values of all the cases are showing in horizontal direction. Values that are higher in red and value that are in lower level among the cohort that are coded in blue color. And the x-axis is showing the probability of prediction. The positive side of x-axis shows the positive prediction, means who died, and the negative side of x-axis shows the opposite prediction, means who survived, the negative class. So here our positive class was who died. So the values are showed in such a way towards the right side of the x-axis, means the positive side values are pushing the model to predict the mortality class, means the positive class, towards the positive hand of the x-axis. So if we see SOFA score, the higher SOFA score was associated with the prediction of mortality, and who survived, their SOFA score was lower. So in the left hand side, means the negative portion of x-axis, the blue values are falling. So in this way, PT, we can interpret the more reddish values are in positive side. So higher PT was more associated with mortality group, and lower PT was associated with survived group. So in this way, the interpretation tells three things: how the data distribution is there, how the positive or negative side of values are associated with the positive and negative classes, and the priority of the features along the y-axis. Who was better to predict, it is at the top, and who are successively the lower important features. So three information is clubbed together here. So it is little bit complicated to interpret, but it is giving more information compared to the bar chart, where only we have the SHAP value, means the priority score for the prediction. So with this interpretation of the x-axis positive and negative class probability, and the distribution of parameters for giving towards positive and negative prediction, we will come to the next concept of SHAP, dependency plot. It is not very commonly used, but it is also a very important for interpreting a single parameter in the cohort. So what it is telling, in the x-axis, the parameter value is shown, and in the y-axis, the SHAP value for that parameter is shown. Here you can see value of SHAP is going from positive to negative. So at 0, there is some threshold for giving the prediction towards positive or towards negative side. So here, if we see at the level of 0, 0, where SHAP value falls, and we draw a horizontal line, we can check at which value of age it is a cutoff value for giving a mortality prediction or a survival group prediction. So from this dependency plot, we can identify the threshold value for each parameter for this classification problem in our cohort. So in this way, we can interpret sex is a binary variable. So for 1 and 0, there is a distinct distribution. We can tell 1 was male and 0 was female. In this way, it was coded. So female was more towards the mortality side. It was seen in this sample, female had more number of mortality than the male. And for weight also, if we draw 0 0 horizontal, then at somewhere near 55 maybe, there is a threshold we can draw for mortality and survival prediction. So in this way, it gives a conceptually understanding the data and the threshold value to draw a line for mortality prediction. This is for clinical understanding how the model is understanding the data and how the classification probability is coming out with this data set and the values. Is it clinically acceptable or not? So this is also a kind of interpreting the model's understanding of data, means the distribution of data, how it is handling the data to identify the classes. So this is also a important SHAP concept. Yes, SOFA pulled almost everything. SOFA is a composite scoring system. It has many parameters. Yes, yes. This is for the model, and we have checked only SOFA how it is giving the area under the curve, and the machine learning model how it is giving. So it was little bit 3 to 4 0.3 to 4 higher by model. So it was giving marginally better, not very good, because SOFA was pulling almost all the information. Uh, One thing is refinement is needed. Another one thing is more sample size is also needed. So it was a cohort who has GI surgery, major GI surgery only. So across different patients, maybe they are for other complications, infection or other thing. So for the small cohort and in a very restricted area, it was giving the result. So it is in general, it is telling very difficult to what was the issue, because sample size was nearly 500, not large. So now the major part that was remaining for the imaging data that we majorly used for model development using CNN, convolutional neural network. And that is the major area where the deep learning works as a black box, and we don't know how the features are extracted from image. So it is a very important part to understand how the explainability comes into the picture for clinical reliability. So the top panel is showing a black box model. It is for a COVID data set to identify the person having the COVID related infection or not using X-ray image, sorry, CT image. So in this image, top panel is showing COVID infected was yes, the input image is given and it is giving yes. So it is a confusing black box thing. But when the explainability come into the picture, it tells about the area. The main idea to give the particular area of the image, which is the reason for giving this prediction. So the black box model with post hoc XAI and intrinsic XAI model. So two things, like in the last class we saw, it may be post hoc or anti hoc. Anti hoc means when the model is trained on the data set itself, the explainability is incorporated during the model training. And post hoc is after development of the model that is finished. Then we can use a data set, use the trained model, and we can have the explainability component from the result. So that is post hoc. That can be calculated from a single data set we can use any of the data set randomly to have the explainability. Anti-hoc means we are whole data are using for model training and explainability incorporated during the model training itself. So in both the cases, what is done, the identification of the exact area that is the reason for the model prediction, that is highlighted in some way. So it is transparent. Now it can be clinically identified, reliability is increased, and it is more acceptable. So how it is done, we will see. Lime and GradCam, these two terms maybe you have encountered frequently when you will see image-based deep learning method models. So LIME is local interpretable model agnostic explanation. It's a long name. So LIME is very commonly used. It is after model prediction, means input data, then black box neural network, CNN, whatever the model we are using, that is trained using the data and model prediction is done. Then the model is used for build the explainable model on single prediction. Means single data set is taken. It is with the model, the explainability is built. So with an example, it will be very easy to understand. For example, an illustration is to generic step involved in the perturbation based explanation. So what it does, it is from the problem of identifying cat or dog in the whole set of input images. I have taken this simple example to understand the process. So in the image, we just skip some portion of the image and we give all this means deformed images in the model for prediction, and each image will have a prediction value probability. So where the prediction is very low, means which portion of the image is not present, and for that reason the model is not uh, giving the proper output, then the interpretation is that portion was most important portion of the image, because the missing portion is giving the probability of prediction very low. Otherwise, if the missing part are in different sectors, the prediction is almost similar, the positive, it is a cat. But when the face is missed, it is wrong, the prediction is wrong. So from this result we can interpret the face is the most important part from the input images to identify whether it is a dog or cat. Means we are doing some modification, some deformities in the input images, and see how the probability is changing with that deformities. If some deformity is giving the wrong answer, when it was present it was something totally different, then we have to understand that was the main factor, that area was the main factor for giving the correct prediction. So now see, this is a chest x-ray and the perturbation examples are there to understand whether this CT or X-ray image characterizes the onset of COVID. So these black areas are the number of area of perturb 125 to 50. It varies. Number can vary. The area randomly picked up from the images from different places. And it is a lot of input images created by this process. And all the probabilities are assessed without this deformity and with deformity. And by comparing the probabilities like prediction probability, the area is identified. Here, the highlighted area is red, yellow is the highlighted area. This is the color code that is used. Which part is most useful for this prediction? So in this way, the areas is identified how it was pushing towards the prediction. So this is another example from a paper 2020. It is for the prediction of Parkinson disease. Yes. So the area is identified in this lower image, and the prediction was done by which images had Parkinson disease, and the area which gave the probability that is highlighted here. So now I'm showing GradCam. This is similarish type of heat map. It is called GradCam heat map because it uh, shows the highlighted area by this heat map. The more means the red is the higher value, and towards the blue it goes lower importance. The red area is the most important part of the image to have the prediction. So these are all different type of brain tumor and brain pathologies, and glioblastoma or the meningioma, all different area. The radiological image, the radiologist can be better understand how the problem is here, and heat map is actually showing the exact area. Means this middle portion is middle column is showing the heat maps that is generated by the model. Means this area, after extracting the features, when the neural network, deep neural network is being trained, which means you have to remember the filtering method for this problem. Filters was the intrinsic factors in the CNN. What filters means, it is capturing different features from different areas. It is capturing the features. Then the features where it is important, it is calculated by the model by through the training and back propagation, which parameters means which feature is important, and ultimately that will go for the prediction. So in this total loop, which part of the image that is giving that important features, that is picked up actually. So the heat map is generated in that way, which portions features was most important for the prediction, and then this map is overlapped on the input image, so that the problem, the where the actual pathology is, it can be seen and understood. So for every input image, it is a anti-hoc model. So for every input image, the how the features is giving the importance for the prediction, it is trained by the model, and the heat map is generated for each and every input image. It can be generated, and for each and every input image, it can be overlapped and see how the input image was used for the model for this prediction and whether it is clinically correct or not. So this is very commonly used explainability process for CNN based model when the CT or MRI image or medical, any kind of medical images are used. So this is very important and commonly used method, GradCam. So when and how we will use the explainability? The risk level determines the need for explainability. Where the risk is very high, like ICU sepsis prediction or anesthesia drug change during the surgery. So these type of things are very highly important risk associated situation. So here the explainability is very, very needed. And when there is lower risk, maybe routine diagnostics or some other kind of diagnostic, this may not be that much important. So when we will use AI model, so depending upon our risk factor, we should go for the explainability. When to use explainability, that we should remember. In these high risk areas, we must have the explainability factor before using AI model. So that factors, explainability means the explainability process, whether it is SHAP or GradCam depending upon the data set and the adequate number of data set for validation, prospective validation of the model. All these factors come. The generalizability of the model means across variety of data set it should be used for training and testing. So all these factors come into picture. The explainability is not exactly the one thing. Actually, it is a whole umbrella of ideas. So this has to be ensured before using a model and taking the decision from the model actually. So the challenges in explainability is the sharp line explain a approximate thing. It is not the actual model logic. So when different set of data set is used or some other, when it has random effect also, when the different models means if we are using tree based algorithm or if you are using some other type of support vector meshing algorithm, for different algorithms the interpretation may change. It may not be different for top 5 parameter, but if we will see in the SHAP list for the top 20 features the order may change depending upon the model intrinsic logic. So it is not very convincing all the time. And another thing is the human interpretation gap. So most user glance at the top features, find it plausible and move on. Means the top features, maybe top 5 features are clinically adequate, but model is using maybe top 25 or 30 features. So how it will be handled clinically and reliably, that is a question. Means the explainability is there, but it is not still adequate to some extent, whether when the very high risk factor is associated, whether we will go with it or not. And LLM model, the generative AI model, are still a black box. There is no explainability associated with it. We cannot find how the prediction of text means the next word, next sentence, how the result is given, that we don't have any method to understand it till now. So the trustworthy ecosystem involves many terms: fairness, responsibility, transparency, interactivity, interpretability, explainability, robustness, scalability, and satisfaction. So all these factors are all together, they are all interrelated, and all these things has to be addressed for making a AI model trustworthy. And it's a long iterative process. Suddenly we have a small data set and we have made a model, that does not mean it is clinically usable now. So it is a long process for clinical validation, explanation, constant monitoring over the period of time, and then to approve it by the government regulatories, and then it can be used in the population. So key takeaways are the in last class actually it is in continuation. So I expect most of you are remembering things. The For model performance evaluation, we discussed F1 score precision and recall is very important, not only the accuracy. Along with the sensitivity, specificity, and area under the curve, this F1 score is very important factor for class imbalance when you are doing classification model. So, and the decision curve analysis and for clinical utility is very important in our domain. The explanation is not equal to accuracy. It is a logical, plausible explanation how the model is working, but it does not infer the accuracy of the model. Accuracy has to be assessed separately. Explainability has to be assessed separately. Two things are separate. And if a model is black box and still it is in controlled way, it is used with explainability and all, it can give a important clinical insight. So for a black box type of deep learning model, we should not be very means we should not hate it as it is a black box. It can be useful with explainability factor. It can be acceptable. And data quality is important, not the volume. And when, where, and how the model was developed and tested means that generalizability area has to be checked before using the model. And the final is the clinicians who are the accountable, who are the most responsible for using AI model in clinical sectors. So their decision is the paramount. So this was the last class, and today another class I will start and conclude also, because we will have time. So this class is not this means it can be covered quickly, because healthcare data handling is something that everybody we are doing already, we know. But some little bit technicality I want to add here. When we are using our data set for AI model, some points need to be taken care of. So this, there are some small little bit carefulness that will make our work very easy actually. So data is of different types and at different time points. Longitudinal data is there, and data can be structured, means tabular, imaging, text, and multiomics. Different type of data sets are there. So for structural data and unstructural data, uh, when we see, structural data is mostly commonly we use, but these days unstructured data covers almost 90% of the healthcare data. So the analyzing unstructured data and combining this with structural data is a current need of the hour. So for this, the ML model, deep learning model works best actually to combine the multimodal things. So we already have the idea how unstructured data is difficult to store and handle, and it needs standardization in many ways. We'll see quickly. So so one thing we should remember, the garbage in, garbage out phrase. If our data is not good, our model will not be good. So we should have a good quality data, and for this we need to check some points. So one thing is how the data quality, how good is the data, and another point is the quantity, how much sample do we need. I have been asked how much sample is required for a thesis, or how many sample is required for this type of problem. So there is no gold standard for it actually. So in literature, there were many studies how much data is enough for a machine learning model or a deep learning model. So some study has shown beyond 1,000 sample, the machine learning model do not improve much. So 1,000 sample is enough. Some study has shown it depends upon the data types, what is the data, and what is the model, and how is the class balance is there, how many class imbalance is how much. So it depends on many things. So there is no rule of thumb. Mostly in thesis, maybe few hundreds, 400, 300 data set will be adequate for a good analysis for a uh, basic live model, means the prototype model. Actually, power analysis when we do the conventional stats, but for machine learning, this is not the case, because it is training and test split is there. It is differently handled by the different algorithms. So for machine learning models, we have sample size calculation algorithm. We use that algorithm. So the power alpha error, beta error, and power analysis, that does not work very well with ML model sample size. So there are many challenges like diversity in population, connection site, tool, what machines are using, and it is a costly, time-consuming process. So in to solve this, there are many open source database available these days, basically for unstructured data, what is not quietly available, and majorly the ground truth marking means the prediction class, whether it is tumor, malignant or benign or some other thing, that clinical ground truth labeling is a very costly, time consuming thing. So for this, open source data can be used for an initial level of analysis. So that is there. And some data collection points are the standardization of process. Means when we are doing some data, uh, even for any blood report or any kind of culture, the standard unit has to be there across the center or across the machines. So it should not be like means the millimole or how the measurement is done. It should be, the unit should be across the all system, all center, it should be same. The unit should not change frequently. So in the Excel sheet, the value will totally drastically will be different otherwise. So binary consistency is when it is yes or no type of data. So when we are putting our data set, if we use 1 and 0, it will be very helpful because machine understand 1 and 0. If we were entering yes or no, it is no problem, but we have to process that for 1 and 0. So when we are using binary or categorical or ordinal values, then we can use the values 1, 0, 1, 2, 3, 4 like that, so that it is more easier for the next level of programming. Having a word for categorical variable or binary variable is not a problem. But one problem is there for yes, no, sometimes we in hurry we write y, and for no we write no. So for a program, yes and y, these are two different things. Machine don't understand y means yes. So when we are doing the words, using words for some category or binary variables, we should be very sure we are exactly typing the same word correctly. For numerical data, the units and the heart rate values. Another thing, when we are writing our BP, almost everywhere I have seen, we write the diastolic slash systolic in this way. But machine don't understand this slash kind of thing. That should be taken in different two columns. Diastolic, one column, systolic, another column. These two is different value. If we are putting a slash, it will be read by the machine as a text. It will not be a value. So this type of small technicality, if we follow during our data entry, then I will request all faculties to direct their students to fill in this way, so that afterward it will be very helpful for analyzing the data. And when there is no value, do not write a 0, because 0 is a value. You write NaN, means not a number. That is understood by the machine. When it is not a available value is there, please write NaN, capital N, small a, capital N. This is the machine interprets not a number. Means that is a blank, nothing is there. So don't put a 0. For date and time, be consistent for the order. YYMMDD is the standard across different systems and algorithms. So this is the format that should be used. It should not be right like May 4th, April 5th, it is a very confusing thing, and many rows may have many different type of value. So when we type it, we don't remember. We just want to type it and we want to finish it. Plus, little bit of time will actually save long manual type correction afterward. So please remember these small technicalities. And for timestamp also, for some type of data set, when we are taking a small duration data set, like continuously monitoring some parameter, then this timestamp also comes into the picture. So HHMMSS is the format for storing a time value. It is not like uh, 5 p.m. 6 means 5:20 p.m. 5:10 a.m. It's not like that. So this should be the format, and it should be in format of 0 to means 24. The hours will be in that format. PM AM is not the correct form. So when the date is stored in that way and time is stored in that way, the calculation of delta of time is easier in Excel sheet. So there is formula can be used in programming also. If it is stored in a structured way, the delta parameter means the difference between time and date can be correctly actually calculated. So this is the purpose. So this is a summary. So patient age 65 years. If you are putting years with 65, it will not be a number. It will be a text data. So please write only 65. Don't Y or years something. Year will be at the top in the column heading. What is the unit you are measuring? So normal is a vague code, 0 or 1 or some value. The date is in the format, and blood pressure means that I have already discussed. It should be differently stored. So, and always have a master copy of the raw data, and whatever you want to change, you make a copy of it and change it. The pseudo ID means it may be, uh, it is not a very means conventional thing, sir. It is 1, 2, 3, 4. We can just for our interpretation, we can change it as a serial number 1, 2, 3, 4, because we cannot use name and user ID. सर ये HIPA एक this is a sub terms actually I could not recall the for this is a regulatory. Uh-huh. So uh, yes sir, all this has to be removed when we are giving the data set for analyzing for anyone. Huh. So master chart will have all this data, but when we are analyzing it, everything will be removed. 1, 2, 3, 4. So 18 HIPA is a regulatory term, sir. This is used for the identifiers. Yes, ethical aspect of. Yes. Yes, sir. So address, phone number is very much identifiable. The person can be identified the phone number. So in unstructured data, the imaging and text and signal means the ECG or EEG, these signals come into this area. all from all wearable devices. And these are all some challenges: quality of storing the data, high storage is required, difficulty in analysis because of the data uh, type itself. It is a time consuming process, and security also, because each data will have, maybe in a x-ray we have the patient name, age, everything is in that film itself. So sometimes we have to mask that areas. So here in this all these slides, two things need to be checked: how the data should be stored. Text should be stored in .txt format. This is the file extension, or JSON is a type of file where text data is used as to store. And pre-processing part is not for your area actually. And for signal data, this is the file type .edf or .hdf5. So you have to check your instrument what is the data type available to store the data. And across all the data, every file should be stored in same manner, so that when we will analyze it, it should be pre-processed. When after capturing the data, how the data is visualized, it needs some pre-processing. So the each file extension also have some compression algorithm in behind it. So what we are using to save the image or signal, that is very important. So there should not be some data loss. So for example, if we are seeing a voice data, it should be WAV file. There may be some other format, MP3. That is very commonly we maybe know. We in mobile music and all, MP3 is very common term, but it is a compressed data. It lose some information. So for research purpose, WAV is a very commonly used format. So this small technicality we should remember. For images, DICOM file is the common file format for all type of image, CT and MRI, and it has all the information, the rich information that the CNN model use actually, that is needed. So DICOM image is required for the analysis. We cannot take a screenshot from our monitor or laptop, and we cannot use that screenshot for a deep learning model, because the models use each pixel information, and DICOM file have that level of precision, and that voxel is associated in the DICOM image. So every voxel have some height, width, and the associated parameter, means it may be Hounsfield unit, it may be MRI signal. So that takes lot of information. When we are taking a screenshot from a DICOM image from our computer, it does not make any sense for CNN level of analysis. So for a image data, we must have the DICOM format file, and that file is converted programmatically for further processing. So DICOM is the file format that we need for CNN analysis. So, and for pathological slides, the processing means the processing of the culture and how the strain is using and how the images are captured, what will be the size and resolution, that should be standard for all the cases. It should not change, it should not vary. Otherwise, the analysis is at the level of pixels. So how much resolution we are taking, that is very important. If we change across the sample, it will totally crash the whole analysis process. And for retinal scan, the storage is .jpg or PNG. This is high quality, and this is simple one single image, so it is not that complicated like DICOM. And for video data, the storage is MP4. When we are talking about ultrasound video or the endoscopy video, we can store the video in this format, and it is the standard process for further processing. So the metadata preservation is very important. Like metadata means the information of data. When we are having DICOM data, it has metadata. How much pixel size is there? What was the other parameters like MRI imaging protocol? Everything is stored in the metadata. All factors are important for the analysis. So that should be preserved. The artifact removal means there the noise and all these things, all these are removed before, means you, this is not your part, but you should know there is artifact also, but you should not discard the data. Means CT or MRI may have some artifacts and it can be handled to some extent. If it is not usable, it should be, later on it can be rejected, but otherwise there is noise and that can be handled by program. So all data has to be kept very safely. And anonymization is very important thing. Before giving the data set for analysis, we should anonymize the data set. For CTs, for MRI, for any kind of data, the metadata have the patient information, the scan date, everything. So UHID, everything have there in the metadata. So when we are giving, we should anonymize it through the software so that the information of imaging will be there, but patient information will not be there. The identification will be not there. Okay. Yes. Sir, this area I have not ever encountered actually. I need to look into that area actually. So I you don't know what is the standard in ML analysis. I will check that area. So the data pre-processing have these two major area, risk of bias. Already we discussed in the last class. We should cover different variety and different type of regional, geographical, all whatever the possibility of variety is there, we should collect all these things. And the bottleneck is the ground truth annotation. Means for classification model, we have supervised model, we have the label first. So this area, this expert bottleneck is the major area where it needs long time for the clinician to give that ground truth level. Levels means the class levels, whether it is benign or malignant, whether it is a high risk or low risk or grading, anything. So this area is a problematic part. When it is done, 90% thing is done. So data annotation already, I think we have discussed how the area of image, the region of interest is drawn in the image. So it may be a whole anatomy like liver here, or it may be some internal area of tumor or fibrosis that we want to analyze. So it can be for a bounding box, like to just tell the here is the nodule. So this is just detecting a nodule. But if we want to have the total area of the nodule, then this segmentation is needed. For detection, only this bounding box is enough. So this part is in the lung axial size slice. This part have some pathological problem. So this is detection level labeling. When we need a exact area of the tumor lesion, then we have to have the total area under the ROI, region of the interest, segmented out. So we have to draw, means we have to label it in that way. What is our output? So it's a challenging thing, you all know. Time consuming, expert input, experience, and uh, different or more component, means maybe consensus labeling is needed for inter-rater variability assessment and all. So lot of aspects are there for this labeling part, and challenges are there. And for missing data, there may be data missing for different reason. So for unimodal and multimodal missing data, the color coding is showing the different modalities. For each modality, one color is used. So there may be scattered way missing data. Data can be missed during different variety of scenario actually. So patient may not be present, or patient may be dropped out. For that, data is missing. Patient may have very critical condition. For that also, it may be missing. So two things are different. When patient is in high, means to the why is the question here, why it is missing. So MCAR is missing completely at random when patient is not available. MAR is missing at random, means sometimes it is there, and means for some data it is available and not available, and missing not a random is the major problem because of the severity of the patient, and it was not able to attend the test, or it was not possible to make the examination. So this missing are a very important parameter for model itself. It tells the risk already there. This patient has already, that missingness is not a simple missingness. So that is very important when a patient is in so severe condition, so that the data is missed, we should not discard the sample. We should remember that is already a flagged patient for high risk. So from the beginning, when we have this type of missingness for high risk cases, we should not discard randomly. Like it has not completed the whole data set, it is of no use. It's not like that. It can be handled in different way with a red flag, high in alert flag. So that this missing data can introduce some bias also. So this is handled by the model imputation. The MIC multi iterative, I can't recall the full form. It's an iterative process and machine learning algorithm. This advanced imputation MICE method is a machine learning method to handle the missingness of data. So whatever sample we are having in missing cases, missing parameters, we should take off everything intact so that it can be later on handled. At your level, you should not discard. And this imputation can be handled in different way. There are multiple methods, and I think I have almost covered everything, sir. So these are all. These are all very technical things that I don't think at your level you need to actually indulge in. So for another idea, the missingness can be at multicentric level. Maybe one single modality is also missing. So in this lower example, for some centers, some data set may be available. Some other hospital may have some different modality. Means the modality 2 and modality 3 is completely missing at single one center. So for this type of scenario, the data is not usable. It is not like that. The model can be used, maybe developed with the common data set, and some post hoc analysis can be done with the available data set in a subcenter basis. So data is very important, like a gold mine. We should not discard the data just like that. Every data, every sample is important. always there is some mechanism to incorporate each and every sample actually. Thank you, sir. So I had some hands-on also. So these all for student actually, how to enter in the Excel sheet, how to make it more handy and less erroneous. So there is some mechanism to storing Excel sheet. This was mainly for students, sir. So
All of us are students.
okay, sir.
This is a good thing.
So okay, then I can. If time is there, sir, I can then carry.
I think we have to say what I've learned is that we should have the prevention of missing data. We should use the international way of entering date, and we also have to have a complete data center or data unit. So from beginning, we don't make mistakes. So otherwise, this will be uninterpretable, a lot of missing data. Well, any other comments, Dr. Tiwari?
Mm. Mm. Uh, no, sir. The ethical clearance is not required for doing AI analysis because when we do AI analysis, first thing we do it in locally. The data analysis is not at all connected with the internet system so that it is shared globally. It is always we keep the data analysis local in our system. First thing, and when we do the analysis, we don't use the patient information. It is not required actually. Only the values, the parameters are used. So there is no need to have again ethical clearance for this. Thank you, sir. So next class we will have a quiz and it will be fun only. It is not a difficult thing. We will have fun.